So continuing on our studies of the solar system, you've already covered the terrestrial planets, right? These inner planets over here. I'll get my pen out. Okay, so we've covered these are our terrestrial planets, and now we're going to cover these large planets out here, our Jovian planets. So remember in the temperature scales worksheet, we talked about the different temperature scales. And I just want to kind of reiterate the differences here for you guys. So we're used to Fahrenheit scales in the United States. Okay, we're used to looking at things in Fahrenheit. So, you say, oh, it's 60 degrees outside right now. You have a good idea what that means. The rest of the world tends to use Celsius, and science in general uses Celsius. Okay, but then astronomy, okay, we talk about extreme temperatures. So we're going to measure most things in astronomy using Kelvin, which we call this the absolute temperature scale, because at 0 degrees Kelvin, okay, so look down here, 0 degrees Kelvin, that's the coldest that anything is ever going to get. So this literally means this is the point where atoms and molecules stop jiggling. Okay, so it's so cold that the internal structure of everything around us stops even having microscopic jiggles. So even outer space, or we think of that being like the coldest anything can get, that is even a couple degrees Kelvin. It's not even at 0 degrees Kelvin. So 0 degrees Kelvin is the coldest anything can get. So notice up here just our differences here. Oopsies. In terms of the freezing point. So freezing point of water, if you recall from your temperature formation worksheets, that 273, right, is the temperature at which water freezes in Kelvin. That's 0 degrees in Celsius or 32 degrees Fahrenheit. And then similar for boiling, okay, 100 degrees Celsius or 212 degrees Fahrenheit, and then 373 for Kelvin. So we were mainly looking at the freezing point of water for that worksheet because that's the point that essentially we can divide our outer planets from our inner planets. So if you want to know how to do this conversion, now you will not need to know how to do this for the class, okay? But just if you're curious, this is just a little cheat sheet for you if you want to know how to do conversions between, let's say, Fahrenheit, or from if you had Celsius, how to get back to Fahrenheit, or Fahrenheit back to Celsius, or if you have Celsius to Kelvin. So we do not need to do these kind of calculations in the class. Just in case you're curious how to do the conversions, here they are for you. Okay, so let's dive into our outer solar system. So we'll start with the big ones, Jupiter and Saturn. So in terms of our naked eye observations, or with smaller telescope observations, what would Jupiter and Saturn look like? So you can definitely see Jupiter and Saturn with your naked eye. In the night sky, they're going to look like really bright stars. They're going to look brighter than most other stars around. And so that's going to be one clue for you to see that they're something different, perhaps. Once we get a telescope, even a small telescope, we're going to be able to see some really distinct features. In Saturn, you're going to be able to see the rings around Saturn. And then in Jupiter, you'll be able to see the kind of gas clouds. Now this is probably through at least like a 16-inch telescope or so, but you really sometimes can, even with small telescopes, you can see these dark bands, and you can tell that there's something else going on there, right? Okay, so let's do a concept question. So you can only see Saturn in the early morning and early evening. So remember with our terrestrial planets, we talked about sometimes you can only see certain planets in the morning or evening. You can't see them at midnight. So why would this be? Think back to our studies and then see if you can answer this question. So pause the video and think about it. Okay, so hopefully you thought about it. So you can only see Saturn in the early morning and early evening. Is this true or false? Hopefully you answered false. So if you remember our studies from a few weeks ago, that Saturn is what we call a superior planet, which doesn't mean it's better or worse. It just means it's outside of Earth's orbit. Okay. The inferior planets are the planets that are inside Earth's orbit. So the superior planets can be seen early in the morning, early in the evening, and all through the night, okay, just depending on the position of its orbit in relation to Earth's orbit around the sun. It's Mercury and Venus are the ones that you can only see in the early morning and early evening. Okay, so what about the basic structure? So both Jupiter and Saturn have similar structures. They're both mainly hydrogen and helium, okay, approximately 71% hydrogen, 24% helium. Okay, they have rocky and icy cores, with these areas of what we call liquid metallic hydrogen and liquid helium surrounding them. Okay, so that's kind of like our liquid mantle of iron on the Earth. But Jupiter and Saturn have something a little bit weird. It's called liquid metallic hydrogens. Okay, so it's where hydrogen is not quite solid yet, but it's not really gas. It's this weird metallic hydrogen. They both rotate quickly, so the planets are actually somewhat flattened due to that angular momentum that we talked about with the formation of our solar system. And they're both still cooling, so they do radiate some energy. So effectively, they are glowing a little bit because they are releasing energy still, because they're still cooling off from their initial formation. Okay, what about the atmosphere? So both have very thick atmospheres. Okay, so we talk about the visible surfaces of these planets. We're really seeing the top of the clouds when we talk about the visible surface of these planets. They both have rapid rotation and convection cells, which twist those clouds into dark belts and light zones that are parallel to each other and parallel to the equator. Okay, so that's what those stripes along Jupiter are. Okay, those generate really high-speed winds on both of these planets. I'm sure you've heard and you've seen that last image, the great red spot of Jupiter. Okay, this great red spot right here. This is a large storm on Jupiter, okay? And we actually see it grow and wane in size. Okay, it has been there for hundreds of years. And that varying in size I mentioned, it can vary from like the diameter of 3 Earths put together to 1 Earth put together. So this storm is bigger than the size of Earth most of the time. We've noticed that it rotates counterclockwise in a period of about 6 days. And it's not the only storm system that we see on Jupiter, okay? There are other storm systems. Sometimes we see them as these white ovals. They seem to be these long-lived southern hemisphere storms, or these brown ovals, which are actually a little bit different. They're holes in the cloud cover in the northern hemisphere. Now, Saturn also has storms, okay? We just don't see them as prominently as we've seen this big red storm here, okay? The great red spot, this big storm. Here's some of these white oval storms, okay? And there's those brown ovals, okay? The openings in the clouds a bit. So these red spots are really pretty neat. Okay, here's just kind of a top view, okay? So we talked about those brown spots again. Okay, there's the great red spot, that big storm. Okay, and notice here's a new storm that formed for a while. So Jupiter's atmosphere is constantly changing. Just think of it as one major cloudy storm system going around this huge planet. Okay, so if you want to think about the thickness and the composition of the atmosphere, we have Jupiter's atmosphere on the left over here and Saturn's atmosphere on the right. So notice that on your y-axis you have altitude in kilometers above the 100 millibar level, okay, where the density is so high, okay? And then on the bottom here we have temperature in degrees Celsius. Okay, so notice that Jupiter's atmosphere is a little bit more condensed than Saturn's, okay? Like the cloud layers are a little bit more squished together on the same scale, whereas Saturn's are a little bit more spaced out. So Saturn has lower atmospheric temperatures overall as well. Notice that the temperature scales are a little bit lower here, okay? And Saturn has a weaker surface gravity than Jupiter, so its cloud layers are more spread out, okay? So the difference is that these very compact layers in here, this is mainly due to Jupiter's gravitational pull is so strong, it's keeping those gases very tight, where Saturn's gravitational pull isn't quite as strong, and so it's keeping those same gas layers, see, a little bit more spread out, okay? Okay, so in the visible, right, we're able to see that those white clouds, okay, we call them zones, they're essentially ascending gas. So it's gas rising and it's cooling. And the dark brown clouds that you see in the stripes, those are called the belts, and those are sinking gas, so they're warming up in the atmosphere. And we'll talk about convection layers when we talk about the sun in a bit more detail, but similar to that. When we look in the infrared, okay, so looking in the heat signature, we are able to actually see what's happening here. Okay, so you can see that the belts, okay, the brown clouds, they appear warmer, okay, because they're looking into the depths of the atmospheres. But in these white clouds, so you can see how these white clouds essentially correspond to each other. There's the white cloud there, and there's the exact same white cloud in the infrared, the heat signature. You see it's dark, Okay, so those are cooler clouds. Whereas these brown stripes here, okay, what we call the belts, okay, they're nice and bright in the infrared. Those are very hot clouds. So what about storms on Saturn? So Saturn's atmosphere is very similar. We also see storms. Okay, we've seen a great white spot before, which is kind of some kind of cyclonic storm. Okay, and then what's really cool on Saturn is we've actually seen and heard some lightning. Okay, so I'm going to show you this clip here of actually listening to Saturn's lightning.
We don't really know on Earth why you get thunderstorms at the rate we get them. We look at Saturn, they're very infrequent.
We were pretty sure that lightning exists there, but we actually couldn't see it. It's a giant planet with huge atmosphere, and there should be a lot of weather there.
We had heard the lightning on the radio instrument on Cassini, but you hear static on the radio signal, but you can't pinpoint where it's coming from. We had to use a synthetic noise because the actual noise that the radio instrument is picking up is beyond the human ear. So we picked a noise that sounded like an electrical discharge. In other words, a big spark. That's what lightning is. It's taken us a long time to see the lightning, and that's because normally the night side of Saturn is very bright because the rings are shining down all the time. The night side of Saturn is brighter than Earth under a full moon.
The strategy we chose was to look at the equinox. And the equinox is when the sun is in the ring plane, so it doesn't illuminate the rings that much. And rings become dark, and this night becomes dark.
When it finally got dark enough at night, we pointed the cameras there, and wonder of wonders, there were lightning flashes, and took a series of pictures. And in one picture there'd be no lightning flash, and the next picture there'd be a lightning flash, and at the same time you hear the noise over the radio instrument.
And we actually saw it. I didn't believe it.
The lightning storms on Saturn are very much like lightning on Earth. You get the same strength lightning storms, or thunderstorms. They have the same strength, but they're just much less frequent. I'm enjoying the show.
Okay, so I just thought that was a cool video to show you guys that Saturn has lightning storms. Okay, so I hope you did notice that the sound that they generated, they were getting radio signals from Saturn, and that sound that you were hearing was just fictitious sound just to make it something audible, because as you said, it was outside of our audible range. Okay, so both of these planets have magnetic fields. Okay, they have very strong magnetic fields, and because of that, we see aurora. So we also see aurora on Earth. Okay, that's what we consider our northern lights, okay, or the southern lights. And so these aurora are essentially the atmosphere interacting with the magnetic field of our planet. And so we see the same thing on Jupiter and Saturn. Their magnetic fields, though, are much stronger than Earth's, so their auroras are quite spectacular. Okay, and you can see that here. And much of this aurora is coming from that liquid metallic hydrogen that's in both of these planets. Okay, the rings of Saturn. So Saturn, as the video was mentioning, has a major ring system that actually is being illuminated from the sun so brightly that even during the nighttime of Saturn, when the sun is on the opposite side, it's so bright that it's brighter than the full moon. So Saturn has 3 major ring bands, what we call A, B, and C. But there's many fainter ring bands. And although in images of Saturn, those rings look like a disk, they really are particles, okay? They're essentially just composed of particles of ice and ice-coated rock, and they range in size from a few micrometers, so super, super tiny, to up to 10 meters in diameter, okay? So they're pretty cool. And Jupiter also has some faint rings, okay? So What I mean is, like, when you look at Saturn, it looks like this ring system is like a flat disk, but really you have to imagine those are tons of tiny little particles. Like I said, some up to 10 meters wide, some up to just 10 micrometers. Okay, so you could effectively fly through the rings, okay, because they're just particles. And Jupiter also has a ring system. Oh, I thought I had a picture, but I don't, okay? Okay, so let's do a little trivia question for you. Hopefully you might remember this from some of our last studies. Which planet in the solar system is the lightest, quote unquote, or least dense? I think we talked about this a few weeks ago. Let's see if you can remember. So pause the video, take your time to answer this question. Okay, hopefully you've thought about it, and you remember that Saturn is the least dense object in our solar system, our planet, okay? So Saturn, notice in terms of density, is much less dense than the Earth, okay? So notice our interior planets, right? The terrestrial planets, Earth, Mercury, Venus, Mars, the Moon. Notice that they're all the most dense. They're formed of those heavy rocks and irons, okay? The outer solar system, okay, and of course it's including the sun here, but that's okay, all right, are very low density, okay? They're mainly made up of those gases and those ices. So again, we're seeing that here. And of course, the way to remember this is Saturn's density is actually less than water, okay? It's about 2/3 as dense as water, meaning that technically if you had a humongous bathtub, Saturn could actually float in water, okay? That's how you can kind of remember this, that Saturn is the least dense planet in our solar system because it could float in water with its little rubber ducky. Okay, so let's move a little bit further to our outer solar system and talk about Uranus and Neptune. So in terms of observations with your naked eye, Uranus and Neptune are very difficult to see with your naked eye. Even if you're just trying to see if it looked like a star, they would look like a star, but they're going to be very hard to pick out because they are so far away. And they're very small. So even in the telescope, you're not going to see too much. It'll look very much just like a star. Okay. But once you got a higher, powerful enough telescope, then we start to see something. And we actually have to have missions that go close to the planets, right? Then we start to see more of a planet-looking object. So Uranus was discovered by accidental observations. And then Neptune was predicted from Newtonian mechanics, okay, those mechanics that we talked about in terms of Kepler's laws and Newton's laws of motion. Neptune was actually predicted before it was ever seen, which is kind of cool. So they said, looking at the rotation of the other planets and how they're being gravitationally attracted, we think that there's something else out there. And sure enough, we finally did see that there was a planet called Neptune. So the atmospheres. So both Uranus and Neptune, they're gas giants, okay? So they have very thick atmospheres made up of mainly hydrogen, helium, and some methane. And this methane is what's pretty key in these planets, which makes them different than Jupiter and Saturn. This methane is what makes these planets look blue or green in color, okay? Remember, Jupiter and Saturn, they were more yellowy in color. So hydrogen and helium, okay, these create like a yellow. Oops, sorry, yellow. Ha, that sucked. Okay, a yellow color. Let me write that again. Yellow. I don't have my trackpad yet, so I'm on my mouse. Okay, so hydrogen and helium make a yellow color, whereas methane is going to make that blue-green color of Neptune and Uranus, okay, like this. Okay, they actually look more bluish-green in color than Jupiter and Saturn looking more yellowish. So Neptune has more cloud activity than Uranus. Uranus lacks substantial internal heating. And Neptune is actually contracting, so it is emitting some thermal radiation. Okay, so they both have some storms. Okay, so we see storm systems just like we saw on Jupiter and Saturn, on Uranus and Neptune, not surprising. Okay, so we zoom in. Okay, this is the great dark spot, similar to the great red spot, but this is on Neptune. Okay, it's a huge storm on Neptune. We also see a lot of this long, streaking, high-altitude clouds, which are mainly composed of the methane ice. Okay, and we can see that on these planets, which is pretty cool. Okay, what about the interiors? Okay, so they both have rocky cores surrounded by a mantle of water and ammonia. They both have strong magnetic fields, and the magnetic fields, interestingly, are steeply inclined from the axis of rotation. Okay, so normally a magnetic field, okay, comes out directly around the planet, okay, like this. But Uranus and Neptune, the magnetic field actually comes out like of the side. Okay, it's very weird. Okay, it's a little bit different. So normally it's like this, okay, but Uranus and Neptune, it comes out of the side, which is a little bit different. Oh, and look, I have a better image in my drawing. Okay, so take a look at the various angles. So here's Earth's magnetic fields, Jupiter, Saturn, Uranus, and Neptune. So like I said, on Earth, the magnetic field is pretty much coming directly out of the poles where our rotation axis happens, similar to Jupiter and Saturn. But notice that Uranus and Neptune, the rotation axis for Uranus, notice, is actually very different than all other planets. Uranus orbits on almost a 90-degree axial tilt, okay? And therefore notice that the magnetic field lines are like 60 degrees off from that axial tilt. About 50 degrees off for Neptune as well. Okay, so notice that their rotation axes are a little different. So with Uranus, you really do want to notice that Uranus' rotation axis, unlike Earth's, okay, here's the ecliptic. Okay, remember the ecliptic is just where the planets are orbiting around the sun. Notice that Uranus, its orbital pattern, its orbital rotation is pretty much within the ecliptic, okay? Within the ecliptic. It's pretty cool. Okay, so what does that do then? That means essentially, from your point of view, Uranus is rotating 90 degrees from what we normally would consider. So it's rotating on its side. Okay, so if you looked at how Uranus orbits around the sun, you would notice that it's going to have those extreme seasons. So it's that example of the really exaggerated seasons, because sometimes the north pole of Uranus is pointing directly towards the sun in the summer, okay, and the south pole is directing away from the sun. So they have long winters and long summers. Okay, so very extreme and exaggerated seasons. We do notice that both Neptune and Uranus have icy rings, okay, mainly due to some kind of methane ice. Okay, so you can just see I'm blocking out the image here. And then these are the rings that form around it. Okay, so rings on both Uranus and Neptune as well. Okay, there's Neptune's rings. All right, so let's just do a few review questions. Make sure you got this. So I'll ask the question, pause the video to think about it, and then continue the video to see the answers. So what element in the atmospheres of Uranus and Neptune give these planets their distinctive blue color? Methane. Okay, that methane is what gives it the blue greenish color. Recall that Jupiter and Saturn, okay, it was hydrogen and helium that gave Jupiter and Saturn the yellowish color. Let's do another one. Which planet's average density is less than water? It could float in a bathtub. All right, hopefully you answered Saturn, because remember Saturn's density is less than water, so it could float in the bathtub. It's the least dense planet in our solar system. So remember, density is just how much material you can fit into a cubic volume. Okay, remember back to our overall studies of the solar system? Remember that asteroid belt? The asteroid belt sits between the orbits of which planets? Pause the video and think about it. Okay, hopefully you answered Mars and Jupiter. We talked about that with the formation of the solar system. That asteroid belt sits between Mars and Jupiter. All right, that's all I've got for you guys today. I hope this made sense. If not, make sure you come and ask me questions.